Fundamental concept of quantum computing. What if your computer could explore every possible answer at the same time? Welcome to the fundamental concept of quantum computing. Unlike classical bits, which are either 0 or 1, quantum bits, or qubits, can be both at once thanks to a phenomenon called superposition. A qubit is represented mathematically as ket p psi equals alpha ket 0 plus beta ket 1, where alpha square and beta square are probabilities that must add up to 1. This allows multiple possibilities to coexist in a single computation. Now imagine linking two qubits. When they become entangled, the state of one immediately influences the other, no matter how far apart they are. This opens the door to powerful new kinds of logic. Then comes interference. Quantum computers use it to cancel out wrong paths and reinforce correct ones. It's how quantum logic finds clarity in chaos. All of this happens using quantum gates, like the Hadamard or C0 gate, rotating, flipping, or entangling qubits inside circuits. These are the building blocks of every quantum algorithm. But when you measure a qubit, the magic collapses. It becomes either 0 or 1. That outcome is probabilistic, so quantum computers repeat and refine to get the right answer with high confidence. So, quantum computing isn't just faster, it's fundamentally different. It's about computing with the probabilities of nature itself. Classical versus quantum computing, explained with temperature sensor data. We all know how classical computers work. They process data in binary, using bits that are either 0 or 1. But quantum computers? They work on an entirely different level. Quantum computers use qubits, which can be 0, 1, or even both at the same time, thanks to a property called superposition. It's like holding multiple answers, until you ask for one. Now imagine you have a temperature sensor. A classical system might read 0.43 and log it as is. It handles a single fixed number at a time. But in a quantum system, you encode that reading into a quantum state, like 0.8 ket 0 plus 0.6 ket 1, representing a probabilistic fusion of possible states. Here's the key difference. Classical computing sees one outcome at a time, while quantum computing prepares multiple outcomes simultaneously, exploring them in parallel before measurement. Still, both systems aim to compute and interpret information. Whether in binary or superposition, they both ultimately help us make decisions, like whether the temperature is rising or falling. In short, classical computing is deterministic, quantum is probabilistic, but both can work with the same sensor data, just with radically different approaches. That's what makes quantum computing so promising and so powerful. What's the real difference between classical and quantum computing? Let's break it down with a real-world example. Temperature sensor data. Classical computers compute step by step, feed in 4 readings, say 22, 23, 24, 25, and it calculates the trend using arithmetic. The result, a clear increasing label. Quantum computers, on the other hand, encode the entire pattern as a quantum state, a vector of probabilities, and compare it against ideal patterns like increasing or decreasing using inner product similarity. Here's the catch. Classical output is exact, but it can miss nuances. Input a noisy set, like 22, 24, 23, 25, and classical logic might still say increasing. But quantum computing sees the uncertainty. Quantum systems output a probability score, how close the trend is to ideal. In this case, 85% similar, showing it's rising, but not perfectly. The major difference? Classical computing is deterministic. One input, one answer. Quantum computing is probabilistic. It explores multiple states at once and finds deeper patterns. Where does quantum shine? In noisy environments, large-scale sensor networks, or when the trend is subtle but critical. Bottom line, classical gives you clear answers fast. Quantum gives you rich insights, especially when data is complex, uncertain, or noisy. Where quantum computing will change the game. Key domains explained. Quantum computing isn't here to replace classical computing. It's here to go where classical machines hit their limits. In quantum chemistry, simulating molecules like drugs or catalysts demands tracking quantum states, an impossible task for classical computers. Quantum machines can model these interactions directly. In cryptography, Shor's algorithm can break today's encryption schemes exponentially faster, reshaping cybersecurity and prompting a shift to quantum-safe methods. Machine learning benefits too. Quantum states handle massive data vectors and enable new forms of pattern recognition, faster training, and even generative models. In logistics and finance, optimization problems like scheduling, risk modeling, and portfolio design become faster and more accurate with quantum algorithms like QAOA. And in sensor fusion, from smart cities to autonomous vehicles, quantum computing can process high-dimensional, time-sensitive data to detect trends faster than classical methods. It even extends to physics, where simulating black holes, nuclear fusion, or the early universe requires computing power only a quantum system can offer. From chemistry to cybersecurity, quantum computing will transform industries that demand speed, parallelism, and precision. And it's only just beginning. Quantum computing, its real advantages and hidden challenges. Quantum computing promises to transform how we solve the world's toughest problems, but it comes with both breakthroughs and barriers. First, the advantages. Quantum computers can explore many solutions at once through superposition, giving them the power to solve problems like encryption, molecule simulation, or optimization, exponentially faster than classical machines. In machine learning, they can uncover complex patterns in massive datasets that would overwhelm traditional algorithms. And in cybersecurity, quantum algorithms can both strengthen encryption and eventually break today's most trusted protocols. But here's the challenge. Quantum systems are fragile. They're vulnerable to decoherence and noise, needing ultra-cold temperatures and massive error correction. Add to that high costs, limited access, and very few practical algorithms. For now, quantum is a specialized tool, not a general replacement for classical computing. Quantum computing will shine in solving niche problems, not daily tasks, and will complement, not replace, classical systems. The future is quantum, but getting there will require patience, precision, and purpose. Where quantum computing shines and where it struggles. Quantum computing isn't meant to replace classical computing. It's built to tackle what classical systems can't. It excels in areas like cryptography, where quantum algorithms such as Shor's can factor large integers exponentially faster, threatening today's encryption. In quantum chemistry and materials science, it can simulate atoms and molecules with unparalleled precision, essential for drug discovery and new materials. Optimization problems, like logistics, traffic routing, or portfolio balancing, see real potential with quantum approaches like QAOA. And in machine learning, quantum models may unlock faster, deeper learning for massive datasets. But where does it fall short? Everyday computing, word processing, web browsing, basic arithmetic, classical systems win hands down. Quantum machines are fragile, error-prone, and require ultra-stable environments. They're overkill for simple tasks and unreliable for time-critical applications. So where quantum thrives, security, science, and optimization, classical computing still rules the everyday. Together, they shape the future of computation. Are quantum computing devices available? What are they used for? And when will they arrive for everyone? Yes, quantum computing devices are already here, but not in the form you might imagine. Companies like IBM, Google, D-Wave, Rigetti, and IonQ have built early-stage quantum processors, available through the cloud for researchers and developers. These systems are used to simulate molecules, solve optimization problems, and explore quantum algorithms, tasks classical computers struggle with. But they're far from perfect. Current machines are fragile, small in scale, and require extreme environments. They're built for experimentation, not daily use. So, when will they go mainstream? In the next 5 to 10 years, we'll see real industry adoption, especially in drug discovery, material design, and finance. By 2035, fully error-corrected, large-scale quantum systems could transform how we solve the world's hardest problems. For now, quantum devices are tools for pioneers, but the countdown to practical, everyday quantum impact has already begun. How much does a quantum computer cost? Breaking down the numbers. Ever wondered what a quantum computer really costs? Let's break it down. Building an on-premise quantum device, like those by IBM or Google, can cost anywhere from $10 million to over $100 million. Why so expensive? Because these machines require ultra-cold environments, precise control systems, and elite hardware engineering. Luckily, you don't have to own one. Many companies now offer cloud-based quantum computing. Prices start from $100 to $1,000 per hour, depending on how much power you need and which provider you choose. Specialized systems like D-Wave's quantum annealers, used for optimization problems, also carry multi-million-dollar price tags, but they too offer affordable cloud access. The catch? Maintenance costs are high. These machines demand cryogenic cooling and stable environments. Not exactly your home office setup. But here's the good news. As quantum tech evolves, costs will drop. Cloud access will dominate. And soon, quantum power may become as accessible as cloud storage is today. Where quantum computing research is headed, and what has been achieved so far. Quantum computing research is unfolding across some of the most advanced domains of science and engineering. And yes, we're already seeing remarkable outcomes. First, quantum chemistry and material science. Here, quantum processors are simulating molecules like hydrogen and lithium hydride, an essential step toward revolutionizing drug discovery and battery development. Next, quantum machine learning. Companies like IBM and QCW are exploring how quantum systems could classify data or extract features faster than classical methods. In optimization problems, D-Wave's quantum annealer has already helped optimize traffic in Lisbon and supply chains in logistics and manufacturing. In cybersecurity, researchers are developing quantum-safe cryptography and secure communication via quantum key distribution, already tested in satellites and national networks. And in finance, firms like JP Morgan are using quantum algorithms to enhance risk modeling and option pricing through faster Monte Carlo simulations. In healthcare, quantum simulations of small molecules show promise in accelerating protein folding and drug interaction modeling. And in early-stage research, NASA and national labs are exploring quantum weather modeling to improve climate forecasting. So yes, quantum research is thriving. And while we're still in the early innings, the breakthroughs are starting to arrive. The future of quantum computing and its impact on every industry. The future of quantum computing isn't just promising, it's transformational. In the next 5 to 15 years, quantum computers will evolve from lab-based prototypes to powerful tools that reshape industries. In drug discovery, quantum computers will simulate complex molecules, accelerating the creation of life-saving treatments. In logistics, they'll optimize thousands of delivery routes in real time, far beyond the reach of classical systems. In finance, quantum algorithms will analyze risk, model markets, and flag fraud faster than ever imagined. And in cybersecurity, quantum technologies will force a complete rethinking of data protection, introducing quantum-safe cryptography for a post-RSA world. Research is expanding into AI, climate forecasting, and even national defense. But we're still in what's called the NISQ era, noisy, intermediate-scale quantum, where systems are powerful but not yet fault-tolerant. Yet the trajectory is clear. With billions in investment from tech giants and governments, scalable quantum computing is not a matter of if, but when. So if you're wondering where the next great revolution is brewing, it's in the quantum realm.